Hello and welcome to this chemistry video, the fourth in the series. In this video we'll be calculating the molecular masses of subatomic particles, like the electron and proton. The molecular mass being the amount that a mole of these particles would weigh, if you could isolate them and put them in a bag and weigh them. We'll find the molecular mass of the electron first. We'll use this molecular mass equation. We'll find the mass of a single electron, Me, and multiply it by Avogadro's number, Av, to find the mass of a mole of electrons, and its units will be in grams per mole. Then we'll substitute the numbers in. The mass of an electron can be found in physics textbooks and in Wikipedia. Avogadro's number can be found the same way, and it can be thought of as having units of mole to the -1, because that's what it needs to be for the answer to be in grams per mole. And so evaluating this expression gives us the molecular mass of an electron being very light, about 2,000 times as light as a hydrogen atom. And so now we'll find the molecular mass of a proton, following the same method as for the electron, because all of the information can be found in the same way. And we'll use the same equation. Capital MP is the molecular mass of the proton, and small mp is the mass of a single proton, and this can be found in physics textbooks too. And so we plug all of the numbers into it, like for the electron. And we get this answer, which is practically identical to a hydrogen atom. And it is a lot heavier than an electron. And now to find the mass of a neutron from its molar mass. We firstly use this molar mass equation, like we did in the previous two questions. And now the equation needs manipulation to make the mass the subject of it. And so we substitute all of the numbers in. They can be found in textbooks and more easily with Google. And so we end up with this answer. I've decided to express it in grams so as to make it consistent with measurements made in chemistry. And now to find the molecular mass of a neutrino, being a very light particle. And so we use this equation like we used it before. Small mv stands for the molecular mass of a neutrino. The rest mass of a neutrino isn't known yet, but its relativistic mass is. And that's what's important, because that's what it actually weighs. And so we plug these numbers in, and we get this answer, which looks about 5 times lighter than an electron. Its rest mass is possibly hundreds of times lighter, but because it travels very close to the speed of light, it has a much heavier mass, but its mass is still very small. And now to get the molecular mass of a yellow photon. This is a photon of yellow light. Yellow light can be made of a single photon, because it can strike both the red and green receptors in the eye equally well. So this is its wavelength in nanometers. Here is an equation to get the energy contained in a photon as a function of its wavelength. I got this out of a textbook. The result is an amount of energy expressed in electron volts. If we multiply this amount of energy by this number, we'll get the mass of it in grams, since mass and energy are equivalent. And so if we multiply this value of a single photon in grams by Avogadro's number, we'll get the molecular mass of it in grams per mole. And so we'll write what Avogadro's number is. And then we'll simplify the equation so it will be one number divided by lambda. And then we'll substitute this wavelength in. Notice that it's expressed in meters instead of nanometers. and it is a lot smaller in meters. And so we get the molecular mass of this photon in grams per mole. It has a larger molecular mass than the electron by a factor of 4, even though photons have zero rest mass. They do travel at the speed of light by definition, since they are light, especially the yellow photon, which is a particle of yellow light, and so they do have a mass because they do have energy. And now to find the molecular mass of a green photon, or a photon of green light. We use this same equation that we derived before for the yellow photon. We then substitute all the values in. Notice that the wavelength is now expressed in meters. And so evaluating this expression gives us the molecular mass that we wanted. And now to find the molecular mass of the blue photon. And so we carry out all of the calculations like we did for the green photon. Notice that the blue photon has a higher molecular mass than the green photon. And now to find the wavelength of a photon that has the same molecular mass as an electron at rest. We firstly set these two molecular masses to be equal to each other. We substitute the numbers in. The right-hand side of this equation has an unknown variable in it, which is equal to the wavelength of the photon that we're trying to find. So it's all right for it to be unknown at this stage. We manipulate the equation so that this wavelength becomes the subject of it, and we get the wavelength of this photon in meters. And here is this wavelength expressed in nanometers, and we can see that it's an infrared photon. And here are the relative masses of these particles expressed as the volumes of different spheres. The visible light photons are roughly the same mass and heavier than the electron. I know that this video has more to do with particle physics than with chemistry, but I hope that it gave you a more intuitive feel for molar mass.